Okay, so I'm gonna give you just a couple minutes, like 2 or 3 minutes to actually calculate this. So think about why. So obviously you're going to use L'Hopital's rule, but you should first make sure you understand why am I allowed to use L'Hopital's rule. Make sure you actually answer that question for yourself for each of these parts. Am I allowed to use L'Hopital's rule? The answer will be yes. But why am I allowed to use L'Hopital's rule? And then once you actually do that, also briefly think about how you might calculate these limits without using L'Hopital's rule. That's interesting. So yeah, so I'll give you, say, 3 minutes to think about both of these problems. Caleb, you're all done, just sitting there. No, he's not all done. Well, if you're lost, what does that rule say? All right, so let's look at these. So first of all, so for part A, how do you know? So how do you know we can use L'Hopital's rule? So who wants to answer that? So Caleb, you said you got that. Caleb, how do you know you can use L'Hopital's rule on part A?
Well, direct substitution gives me like 0 for both of those.
Meaning, when you say both of those, you mean numerator and denominator.
Yeah, for A and B.
Right. Okay, good. So for both A and B, if you directly substitute the relevant value of X, you get 0 over 0. Okay, so let's actually make a note of that. So direct substitution of the respective value of X gives 0 over 0 for both parts. So what does that indicate to you? So that automatically indicates to you that L'Hopital's rule is applicable. Right, Hirsch, when can you use L'Hopital's rule? Can you remind us? Now that the theorem's off the screen.
You should use it when there's a
Well,
quotient.
Well, should is a different story. I asked you when can you use it, but so when there's a quotient, right? What types of quotients?
What do you mean by that?
Well, 0 over 0 is one of them. Was there any other type of
Oh
quotient?
yeah, infinity over infinity.
That's right. Yeah, the indeterminate quotients, 0 over 0, infinity over infinity. So, looking at part A. So what does L'Hopital's rule say? Can someone describe it in their own words what L'Hopital's rule tells you to do? Who wants to tell us? Describe in your own words what I'm supposed to do here. Mohammed, you can just use your microphone. We have voices. Oh, he's looking to see if someone, okay. Find the derivative of each function. That she could take the derivative of both top and bottom. Good, right. So both of you are correct. So first of all, I'm going to put a little h above my equal sign to denote that I'm using L'Hopital's rule. Take the derivative of the numerator and then the denominator and then plug in the value. Well, be careful. What if you get 0 over 0 again, or what if you get an undefined expression, right? You have to be careful. So I'm just going to say we're just going to take the derivative of the top and bottom separately. So I get here what? 2x minus 3 over 3x squared minus 6x minus 1. Now, for this particular limit, if I substitute x equals 3, I don't get anything undefined. I just get whatever the limit is, and we're used to doing this, right? So this is just 3 over 8. All done. How else could you have done this? So I asked Hirsch, when can you use L'Hopital's rule? And he started to say, oh, you should use L'Hopital's rule. That's a different story. The should and the can are totally different stories. So should you use L'Hopital's rule for this? Well, what is the other option? What other options did you have? Jessica, you can factor and cancel out common terms. That's right. Right, we have polynomials here. And if I'm getting 0 over 0, that means x minus 3 must be a factor of both the top and bottom. So x minus 3 should be a factor you can cancel out. Now, whether you actually want to do all that is a different story. I'd probably just stick with L'Hopital's rule for that. All right, now let's look at part B. So again, I get 0 over 0. So that means I have to do L'Hopital's rule. Well, I don't have to, but I can. Put a little h above the equal sign. Again, that's to denote that I'm using L'Hopital's rule in that step. You don't have to write the h, but it does help. So let's see, the numerator derivative is e to the x. The denominator derivative is 1 over x. And then substituting in 1 gives me e. So I'm all done, e. What is another way you actually could have done part B, the limit there? Does anyone know another way you could have done that? So it's actually pretty difficult to see. So if you were very, very clever, you could have written it like this. So I hope you agree that these two expressions are algebraically equivalent. Remember, ln of 1 is 0. So if you do the limit as x approaches 1 of this whole thing, you can really do the limit as x approaches 1 of the fraction up top, and the limit as x approaches 1 of the fraction down below. And then you can actually recognize these as derivatives. Use the definition of derivative to recognize the top as the derivative of e to the x at x equals 1, and the bottom is the derivative of ln of x at x equals 1. But that's actually just using L'Hopital's rule. That's just taking the derivative of the top and bottom. In fact, this is actually one of the basic proofs of L'Hopital's rule for a very basic 0 over 0 type limit. It's essentially just the ratio of two limits that are both the limit definitions of derivative for that particular function. That's really all it is. For infinity over infinity, it's a bit more complicated, but for 0 over 0, that's essentially what it is. So that kind of gives you an idea of where L'Hopital's rule actually comes from. Right now, obviously, we're not going to do all that. We're just going to use L'Hopital's rule. But it's kind of fun to see that it's not just some magical, mysterious thing.